When we think about formalizing any mathematical subject, really what we need to be concerned with are the sets of rules that we're going to take to be true that we're going to build everything else off of. These building blocks we refer to as axioms, and very often the way that we think about the axioms are they're the things that have to be true for the world to make sense, the way that we actually make sense of the world. And so when we think about the axioms of some subject in math, what we're thinking about are the truth at the foundation of everything. It's where the study really starts. And so we can think about, well, what are the axioms of probability? And so in order for our formal probability to match the intuitive sense of probability that we have, we need to make certain rules very clear. We need to follow these rules in order for things to actually make sense. And so we want to discuss what are the rules that make probabilities valid and where are they actually coming from. Now, in order to discuss where they're actually coming from, we're going to start with some intuition around what these rules will have to be. And in order to have these intuitions built out, we want to prompt some different scenarios and see if they seem reasonable or not. So imagine first that we have a two-sided coin, and what we say is that it's going to have a probability that it shows heads as 0.7. So 70% of the time it shows heads. The question is, can the probability that it shows tails also be 70%? Can you have something that has two possible outcomes? 70% of the time the first outcome happens, 70% of the time the second outcome happens, and there's never a time where you get something that is both heads and tails at the same time. And if you think about this for a moment, then the answer is going to be no, right? If you want to have the same probability of both things happening, then that probability would have to be 50%. And why is that the case? Well, the problem is that our total probabilities can't actually exceed 1, right? If you think about adding these two up, we're going to have 140%. So 140% of the time something is happening. But that doesn't make intuitive sense with what we know probabilities should be expressing in the real world. And so if we ever come up with mathematical ideas that give us these 140% probabilities, then clearly we've started from the wrong rules because 140% doesn't make any sense to us in our day-to-day lives. Okay? Now imagine that we roll a 6-sided die and consider the probability that we see a 4. Right? Normally we're going to think that there's a 1 in 6 chance that we see a 4, but what if we wanted to set the probability to be negative 0.5? Is this possible? And if again we think about this a little bit, what would it even mean for us to have negative probabilities? Right? There's not really a sense of this. Probabilities are interpreted as long-run proportions, right? And so in the long run, negative half the time we see a 4 come up on this die, right? What does that actually mean? It doesn't mean anything. It has no real bearing in the real world. And so we would say, no, we can't actually do this. Negative probabilities don't actually make any sense. Take a third scenario here where we select a card from a deck of 52 cards, and we consider the probability of getting a king. Now, should we be able to break this down into the summations of the probability that we get a king of hearts, a king of diamonds, a king of spades, and a king of clubs all added together, right? So in other words, if I want to know, well, what's the probability that I get a king? Should I just be able to say, well, what's the probability that I get the king of clubs, the king of hearts, the king of diamonds, the king of spades, add all of those things together, and if I get the same answer, then things make sense. If I get a different answer, things don't make sense. Right? And intuitively, we should be able to do this, right? There are 4 ways that we can get a king, and so we should be able to add up those 4 different possibilities to give us this probability. And so, yes, this should make intuitive sense. Decomposing into individual outcomes should be additive. That's what sort of makes the most sense to us here, right? And so these are intuitions that we probably have based on the ways that we know probabilities should work in the real world. And so what we need to do is we need to take these intuitions and form them into mathematical rules, and those are going to form the foundation of what we actually think of as being valid probabilities. So we're starting from our intuition. We're saying probability should represent something that we have this clear idea of, and in order for that to be the case, we need these different rules, and we refer to those rules as the axioms. So what are the axioms of probability? Well, in order for them to be valid, we have our 3 axioms. They track with the 3 different examples we were just looking at. The first is what we call the unitary axiom. And so the probability that something in the sample space happens is exactly 1. If we want to represent that as a probability statement, we can say the probability of the sample space equals 1. In other words, every time you perform a statistical experiment, the probability that you observe one of your possible outcomes has to be 100%, right? If you flip a coin and you want to say, well, what's the probability that I have either heads or tails? 100%. I roll a 6-sided die. What's the probability I get a number between 1 and 6? 100%. If I look at the weather that it's tomorrow, what's the probability that I experience any of the possible weather conditions? 100%, right? And so we're thinking about this as just saying the probability that something happens is exactly 1. Importantly, it can't be more than 1. And also importantly, it can't be less than 1, right? If we took something and we said, well, the probability of either getting a head or a tail together is 50%, then we have to ask ourselves, well, what happens the other 50% of the time? And because something is going to happen the other 50% of the time, we would need to expand out our sample space, right? So that's not sort of sensible. And so the unitary axiom says the probability of the entire sample space is 1. We must observe an event that's in the sample space. The second axiom is the non-negativity. So all probabilities for any events have to be non-negative. We cannot have negative probabilities. Mathematically, if any event E is taken, the probability that E happens is greater than or equal to 0. Okay, this is true for all possible events E. The last property, or the last axiom that we need to think about here, is the axiom that we call additivity. And so if we take a set of mutually exclusive events, then the probability of their union is the sum of their probabilities. So write this down mathematically. If we're taking a bunch of events E here, right, we take the union over all of these E's, then that probability of that union is the sum of these probabilities. Now, additivity is probably the least intuitive of the axioms, but again, we can think about this in terms of the king's example, right? And so if we wanted to say, well, what's the probability that I either see the king of hearts or the king of diamonds or the king of clubs or the king of spades, right? Because we're doing a bunch of ors there, then what we're saying is that that's going to be the union of all of those events. And intuitively, we should be able to say, well, that's going to be the probability of the king of hearts plus the probability of the king of diamonds plus the probability of the king of clubs plus the probability of the king of spades, right? So we should be able to take that union and decompose it into being addition. Now, critically with additivity, we need this requirement of mutually exclusive events. Remember, a mutually exclusive event is any event that does not have overlap with the others, okay, so that their intersection is the empty set. And the reason that this is important is because if there's actually overlap, then suddenly we'd be double counting probabilities, right? And so if you wanted to know what's the probability that I either get a king or that I get a club, right? We can't just add those probabilities together, because what we're doing is we're saying, well, any card that's a king plus any card that's a club, and we've actually counted the king of clubs twice here. And so we're going to need different rules for dealing with that. But if they're mutually exclusive, then we would be able to add them up. So what's the probability that I get a king or an ace? That's the probability that I get a king plus the probability that I get an ace. Okay, so these are our 3 axioms of probability. Additivity only applies when events are mutually exclusive. So let's think about some examples here. And so in this example, we're taking the events S, C, H, and D to be the events that either a spade, a club, a heart, or a diamond are drawn from a standard deck. So those are all of our suited events. And then we're going to take VJ to be the event that a card with a specific denomination is drawn. So VA would be that an ace is drawn, V2, a 2, a 3, a 4, and so forth, up through Jack, Queen, and King. And all we want to answer is for which of the following events would additivity actually apply? And so we want the events S and C here. And so we want to know, can we write, using the principle of additivity, the probability of S union C is equal to the probability of S plus the probability of C. Does this actually hold, right? And the way that we know it holds is if S and C are mutually exclusive, or in other words, their intersection is equal to the empty set. So is S intersects C equal to the empty set? Well, we have to ask ourselves, is there any card that is both a spade and a club? And the answer there is no. Every card in the deck is either one of the 4 suits, and so there are no spades that are also clubs, and because of that, additivity is actually going to apply here. What about VA and V2? So we're asking ourselves, are there any cards that are both aces and 2s, right? And there is no card that's an ace 2, right? If you're an ace, you're not a 2. If you're a 2, you're not an ace. And so as a result, additivity is actually going to apply here. What about V3 and hearts? So in other words, is V3 intersect hearts equal to the empty set? Is that the case? Right? And here the answer is going to be no, right? Because we can take the 3 of hearts, right? The 3 of hearts is going to be both in V3 and in H, and as a result, we're not going to have additivity here. And so then what we're saying is that the probability V3 union H is not going to be equal to the probability of V3 plus the probability of H. And this does not violate additivity because V3 and H are not going to be mutually exclusive sets. Okay, so we can go through here and we can see, no, the 3 of hearts is in both sets. What if we took all 4 spades, clubs, hearts, and diamonds? Is there any overlap between any of these sets here, right? And the answer is going to be no, right? If you're a spade, you're not a club, heart, or diamond. If you're a club, you're not a spade, heart, or diamond. If you're a heart, you're not a spade, club, or diamond. If you're a diamond, you're not a spade, club, or a heart, right? And so as a result, there's no overlap here. And so because there's no overlapping elements, then we have that additivity applies. Okay, a few more examples. What about V3 and V3 complement? Okay, now this is an interesting question, right? Because we can actually think about this sort of more generally. What if we were to just take A and A complement? And if we think about our complements refer to not A, right? So the complement of A has everything that is not in A in it, and nothing from A is in A complement, and vice versa. And so as a result, A intersect A complement is always going to exactly equal the empty set, right? There is nothing shared between them. Because of this, they're mutually exclusive. And so because of this, additivity is always going to apply. So we can always say probability of A union A complement is the probability of A plus the probability of A complement. Okay? And we're actually going to see that we can say more about this, but that's a lesson for a later date. And so at this point, we can say, yes, additivity does actually apply. Now, what about VJ across all of the different J's? So we're going to take our 13 different sets here. Is there anything that's overlapping between aces, 2s, 3s, and so forth? And the answer is no, right? If you're an ace, you're not a 2, 3, 4. If you're a 2, you're not an ace, 3, 4, and so forth. And so no overlapping elements, so additivity applies there. But what if we take spades, union, hearts, and then take that with the kings? Is there anything that is going to be shared between our spades, our unions, hearts, and our kings? Well, a spade, union, hearts is either a spade or a heart, right? And kings is all of the kings. But of course, we have our king of spades and we have our king of hearts. And so there is going to be overlapping elements. And so no, additivity is not going to apply here. What if we take any single one of our suits and any single one of our denominations? So we take spades with V10, or we take clubs with V8, or we take hearts with the queens, right? Any of these combinations, do any of them work? And the answer is going to be no. There's always going to be an overlap, right? Because you can always take the specific card with the specific suit, and that's always going to be there. And so additivity is never going to work if we mix suits and denominations. Okay? And so very broadly, the axioms of probability are going to codify our intuitive understanding of what makes a probability actually valid. We're going to be able to say that the unitary and the non-negative axioms always hold. Additivity only holds for mutually exclusive events, and so it's important to make that distinction. But ultimately, the axioms of probability really serve as fundamental rules rather than computational rules. We're not going to turn to them a whole lot to do computations of probability, and instead what we're going to think is they're what's sitting under the surface to ensure that the probabilities that we're actually working with match our intuitive sense of probability. And from there, we can actually build up to rules that are more useful for us to actually computing with and working with different probabilities.